Hey, Wheat North, Mr. Yergler here. This video is going to introduce buffers. This is where things start to get a little confusing, but we're going to try and make them as simple and straightforward as we can. Buffers are incredibly important, especially in biological situations or applications. Our blood is actually a buffer, and that's because our body has to maintain a consistent pH, and that's what buffers do. They maintain a consistent pH. If proteins get outside a very narrow pH range, then they denature. They change their shape because they start to protonate different functional groups on the organic molecule, and as soon as they change their shape, they lose their function. So your body could literally not survive without maintaining a consistent pH, and that's where buffers come in. All right, so what is a buffer? A buffer is simply a solution that resists pH when small amounts of acid or base are added. So it's going to resist pH a lot more than pure water. It doesn't resist it forever. If you continually add tons of HCl to it, it's going to change the pH. But it does resist pH when reasonable amounts of acid or base are added. Okay, it's made from a pair of chemicals. So you either have to have a weak acid and a salt of its conjugate base, or a weak base and the salt of its conjugate acid. Okay, that sounds very obscure, so let's look at a few examples. Ammonia, when it's in solution, would make the ammonium ion. And so if we mix ammonia, a weak base, with a salt that contains that conjugate acid, then we would have a buffer solution. Another example would be acetic acid and sodium acetate. If you take a weak acid, like acetic acid, and you mix it with a solution of sodium acetate, you'd have sodium ions in there just as spectator ions. The important thing is you're increasing the concentration of the acetate ion. And that's what really makes it act as a buffer. The reason this works is because when you add an acid or a base, you have both a conjugate base and an acid in there, and so there's something to react with both an acid and a base. Let's look at this example. So if you were to mix acetic acid and sodium acetate, these are the ions you would have in solution. You would reach this equilibrium, right? There'd be sodium ions in there as well. Let's kind of zoom in on that example. So here's our equilibrium reaction. What happens if we add base, for example? What would happen to this equilibrium if the H plus concentration is decreasing because we're adding base? Which way would it shift? It's going to shift to the right because we're dropping the concentration of the product, right? What if we add an acid? An acid is going to react with the conjugate base. So the base, adding a base, interacts with the H plus, and adding an acid interacts with the conjugate base. So you have both in solution, and so it kind of accommodates an acid and a base without changing pH too much. Here's another example. So hydrofluoric acid is a weak acid. So let's say we mix some hydrofluoric acid with some sodium fluoride or potassium fluoride, some salt that contains the fluoride ion. If you add a reasonable amount of OH, what would happen? We would add our OH. Which way would the equilibrium shift? We would be reacting the H plus. We'd be decreasing the H plus, pulling it out of solution as water. So it would react to make more H plus. Anytime you use up the H plus by adding base, the equilibrium shifts to kind of replenish the H plus, and so the pH doesn't change that much. Looking at the same example, but kind of in reverse. Let's say we add a reasonable amount of H plus to the same equilibrium. What happens? Well, you're increasing the H plus concentration, and so you're going to shift the equilibrium to the left, making more HF, so you see our HF will kind of start to increase. But why doesn't the pH change? Because we dumped a bunch more H plus in there, so that it kind of spiked, you could say, temporarily, very temporarily, and then it shifts but kind of goes back to where it was. That's because we have enough of the fluoride ion in there to shift the equilibrium and still maintain a reasonable equilibrium. As soon as you start to run out of one of these reactants, then you have reached what's called the buffering capacity of the buffer. The buffer capacity is basically how much acid or base it can take before it starts to lose its ability to resist the pH. We are going to do several calculations with buffers. If we know the pH of a buffer solution, for example, we can calculate the Ka, or the ratio of the acid and base. Usually you know the Ka, you can look it up in a table. But this allows us to know the ratio of the acid and the conjugate base that are in solution. Now, when that molar ratio is equal to 1, look at this equation here for a second. When your acid and your base are equal concentrations, this ratio would be 1, which means that the H plus would be equal to the Ka, which means if you were to take the negative log of both of those, then the pH is equal to the pKa, and that's basically what's happening at the midpoint of a titration. assuming that there's a weak acid in there. You'd have to have a weak acid or a weak base. Now, I think this equation is the most helpful because it's nice and simple and kind of straightforward. But the Henderson-Hasselbalch equation, which is what this one is way more common, and it's actually on the formula sheet. So you'll have this with you on any test or quizzes. But it's basically just the taking the log of both sides. But I like to use this one because you're just always one step away from pH. The reason the Henderson-Hasselbalch equation is used a lot is because we're often dealing with pHs and pKa's of acids, and so it's a little more clean from that perspective, but it deals with a lot of negative logs. Remember that the P just means negative log. So we're not going to go into any calculations in this video. We'll do another video where we go into some calculations, but I kind of wanted to introduce the idea of what a buffer is, how it works, and some of the formulas that you'll kind of start to see regarding buffers. All right, this is Mr. Yergler signing out.